So, what we are going to do is to introduce some very elementary viscoelastic models here, and I suggest that most of the material that is discussed henceforth in this is based on the classic book on creep and relaxation of nonlinear viscoelastic material written by Finlay, Lai and Onaran. Originally it was published by Northumberland and later Dover published it as a very cheaper edition. Some portion of this material will also be shared as a course material here. So, what we are going to do is, so let us write some basic things about what do we really expect from a material, or what is our understanding of the fundamental feature of any viscoelastic model. So, the first and foremost thing is this particular model should exhibit some kind of an instantaneous elasticity, right. Then this model should also be able to exhibit some kind of a time varying strain under constant stress, and if you are applying a constant strain, there should be some kind of a stress relaxation. There can be an instantaneous recovery, and there is also necessary for a delayed recovery and some kind of a response which is what you can call it as permanent set or residual strain or irrecoverable strain. So, what it means is, if you take a look at it, so this is your instantaneous elasticity that you are looking at, this is your creep under constant stress that you are looking at, and this is the stress relaxation that you are looking at, and we are also looking at some kind of an instantaneous recovery and then a delayed recovery and a permanent set. So, these are some of the basic features of any viscoelastic model that we are really looking at. So, let us try and see whether we could build a model. Now, again to re-emphasize why we should know this, because we yet do not know what kind of a form for J that we need to use. So, for that reason we are going to construct some simple model, and we are not going to get into too much of a complication here. We will work with very simple differential operator method. So, we could have differential operator method or we could have integral representation, but sometimes when we are doing stress analysis, the integral representation can become little bit tricky, but as far as this particular course is concerned, we will stick to the differential operator method, and there are many advanced books, for instance theory of viscoelasticity by Christensen, there is also a book on viscoelasticity by Lakes. So, these books cover more from the perspective of the integral representation, and we will also restrict our discussion only to the one dimensional response. We need to emphasize this point again and again here, because the main motive of this particular course is to characterize the response of bituminous binders and bituminous mixtures, and whatever representations of the mechanics of this material that is needed to explain our characterization technique will only be addressed here. The theory of viscoelasticity is very detailed, there are easily 3 to 4 semester course worth of material that needs to be discussed. We will not get into all those details here. Okay. So, recollect the discussion that we had in the earlier lecture on the use of a spring and as well as the use of a dashpot. We said that the viscoelastic response is sum total of elastic plus viscous, and please understand that we assumed an additive decomposition here. It is not necessary that it has to be additive in nature, and we will ignore what is really called as the inertial effects, we will ignore the body forces, and we will be discussing only with respect to springs and dashpot. There are different types of damper elements that are available. We will not be discussing all those things. There are non-linear springs used, non-linear dashpots used. There are also some viscoplastic elements that are available in the literature. We will not be discussing any of those things. As I repeatedly emphasize, we will be looking into linear viscoelastic response, right. The very first model that is available is the model due to Maxwell, J. C. Maxwell, one of the well known scientists of our time. So, this consists of a linear addition of spring and dashpot in series. Okay. So, we are going to call this as R and we are going to call this as eta, and we are going to subject this combination to a force that will result in a stress of sigma. So, the strain here is epsilon 1, the strain here is epsilon 2 and the total strain is epsilon. So, this is the kind of load that is applied here. So, this is as far as creep and recovery is concerned. One could also do a experiment in which we apply only the stress relaxation. So, now as of now, without even deriving anything, we can actually take a look at this picture and try and see whether one can guess what will be the response of this material. So, what we need to do is not worry too much about the values that are written here, but only take a look at the shape of this material, shape of this particular graph. Okay, right. Do not worry about the stress relaxation graph that is given here. So, it will get little more time to derive this and get involved in this. As of now, you take a look at it. So, if you apply a sigma of sigma naught in this particular form, since you have connected these two elements in series, the spring is going to instantaneously extend, and that is given by this portion, right. Then since the load applied is constant, whatever is the extension that you are going to see in the spring will be attained instantaneously. Then after that, what will really happen? The dashpots starts extending, and if you recollect how we used to draw the picture for the dashpot in the viscous damper element that we discussed earlier, it is going to increase in this particular way. Now, what we are going to do is at this particular point, we are going to unload it at a t is equal to T1, and you are going to see that as you unload it, the spring is going to get back to its old position. So, it will exactly recover whatever we got here instantaneously, and you are going to see that the strain is going to be like this, because we know for a fact that the strain will not be recovered as far as the damper is concerned. Okay. So, now we will find out how to get these values. So, if we have to get these values, we need to do some elementary calculation. Okay. So, we will do that now. So, what we are going to do is we are going to write sigma is equal to R times epsilon 2, that is the model or the constitutive expression for the spring, and sigma is equal to eta times epsilon dot 1, that is the model or the constitutive expression for the dashpot. Now, since we have connected this in series, epsilon is equal to epsilon 1 plus epsilon 2. So, now what you really do is take the time derivative of equation 10. So, it is nothing but epsilon dot is epsilon 1 dot plus epsilon 2 dot. Now, what we now need to do is to substitute epsilon 2 dot 2 you see here. So, we take a time derivative of this. So, that is going to be sigma dot is equal to R times epsilon 2 dot. So, you substitute it here, rearrange the terms, and you are going to get this particular expression. Now, this particular expression is written by me here as the constitutive relation. Okay. Now, this is basically is the expression that you got, and you see that this is a ordinary differential equation, the first order equation in time, and now we start feeling slowly the complexity of this response. So, we are used to writing constitutive models which are explicit, in the sense that you are going to have a dependent variable, you are going to have an independent variable, and all you do is to substitute the appropriate parameters and get the response of this material. But right now what you are seeing is the response is not explicit, but kind of implicit, not implicit in the rigorous sense of the mechanics that is considered, but that it is not straightforward. So, that means for any given loading conditions we need to solve this expression, and only then we will get the actual response that we are really looking at. Okay. So, this is the model form that we got here. Now, how do we really solve this for creep and recovery and stress relaxation? Now, there are different ways in which this expression can be solved. You can solve it in a really rigorous way, because there is always going to be a jump. So, how are you going to get it? So, this is sigma naught h of t. Now, if you try to take the derivative of this, because there is going to be a derivative here, you have to also consider what are really called as jump discontinuities. We are not going to do all those things here. So, if you look at the book of Weinman and Rajagopal, which I referred to in this earlier part of the lecture, a clear cut definition of derivation on how to consider the jump discontinuities are given there. We are not going to do all those things, but rather we are going to do it in a fairly straightforward way. We are going to assume that sigma is equal to sigma naught at t is equal to 0. Ideally it should be t is equal to O plus, but we are going to assume that this is what it is. So, when we substitute and solve for it, this is the expression that you are going to get here. And what do we do for the stress relaxation? For stress relaxation, what do we really apply? For you apply epsilon t, and this is going to be epsilon naught. So, when we apply this particular thing, you are typically going to get an exponential term here. It is fairly well understood. So, if I write it little carefully, you are going to get exponential minus r times t divided by eta. So, there is going to be a some kind of an exponential decay now. So, now let us go back, take a look at this picture, because we seem to have found out what are the values associated with the picture now, right. So, you can actually see how we got sigma naught by r. How did we get the sigma naught by r? This is the strain corresponding to this. Now, you can also check that when you solve this, you got sigma naught by r plus sigma naught by eta times t. You can actually see this particular thing here. And similarly, when we unloaded, we got another sigma naught by r, and then you will also notice that the residual deformation that you see here is sigma naught T1 divided by eta. Okay. So, now we will see how to go about getting that. Now, the first thing is we need to see little more about this particular expression, okay, because this expression seems to be fairly straightforward, because what you see here is a response something like this. That is what you are seeing here. This is given by sigma naught by r, and this expression takes care of this. But what about this expression? So, let us try to do some interesting calculation here, and we will see the following. So, we will take the time derivative of this expression. There is a reason why we want to do this particular procedure now. So, when I take the time derivative of equation 14, you should check it out by yourself. It is necessary that you do all the calculations on your own and check it here. So, you are going to see that you get something like this. The initial rate of change in stress at t is equal to O plus is given as sigma naught by r by eta. So, what it means is, now take a look at this particular figure that you see here. So, this exponential decay was derived by us in the earlier expression. Okay. So, we got what is really called as sigma naught exponential minus sigma naught exponential minus R t divided by eta. Now, what we really want to see is as the time t keeps going in this direction, there is a exponential decay, right. Now, what really happens here? So, there is a jump that is given by r is equal r times epsilon naught. Now, what we want to see is if the stress decays at the fastest rate possible, and what is the fastest rate? You take the derivative of this expression and set t is equal to 0 and find out the slope. You are going to see that this line, it will go to 0 at a specific point, and this particular time T r has a specific meaning in viscoelasticity. Okay. So, what it means is, according to the above, if the stress were to decrease continuously at this initial rate, the relaxation equation will look something like this. So, according to the above, the stress would reach 0 at a time tau r is equal to eta divided by r, and so what is the unit of this? This is Pascal second and this is Pascal, and so the unit for this is S second, and this is called as stress relaxation time. Very important parameter as far as viscoelastic response is concerned. So, this is the stress relaxation time for the Maxwell model that we have derived here. Now, as an exercise you can do this, it will be very easy for you to find out, and in fact the solution for this is available in the Finlay law even around. So, what it means is, when you hit this particular thing, you are going to be able to see that the amount of stress that is yet to be relaxed is going to be only 37% of the peak stress that you saw here. In a sense, this is a very interesting parameter that tells you how fast the material will relax in time. Okay. And we need to understand that since the stress relaxation can keep going forever, we do not know when it will actually go to 0, because this is going to be only an asymptotic solution. So, for us to understand and compare how fast the stresses will go to 0, it is always beneficial to have a parameter that could indicate the variation of the stress relaxation, and that parameter is the stress relaxation time. So, now let us take a look at the another model, very interesting model given by Vogt and Kelvin. So, this has to be pronounced as Vogt and this is Kelvin, Lord Kelvin, right. So, this is the same model, same elements, except that we are now connecting them in parallel. The Maxwell model was in series, this is in parallel, and before we continue I need to ask you a question. So, is Maxwell model fluid? Okay, think about it, right. So, we come to the Kelvin model. Here we are connecting these two elements in parallel here. So, we apply a stress here, and we should be now able to find out what will be the response of this material. Now, since we have connected them in parallel, the strain response is the same for both the elements, but the stresses are going to be completely different. So, again, without even getting into actually deriving the response of the material, we will try and see whether one could find out how the response of the material is. So, let us say we apply a load of this particular form, and this is applied in this particular way. So, there is a spring, there is a dash pot, both are connected in parallel, we subjected to this stress. If there was only this spring, there is going to be an instantaneous jump given by this for the spring alone. Okay. Now, if there was only a dash pot, what it is going to be? It is going to keep it is going to be, if you are talking about the strain, it is going to go something like this, right. Now, when we combine these two things, what will really happen? One will get something of this particular form, what you are seeing here, right. Why is this happening? Because the spring may try to instantaneously extend, but since the dashpot cannot do that, the dashpot will try and restrain it. Now, what will really happen? So, do not worry about this particular thing as of now. What will really happen if we apply this stress forever, right? Now, what can happen? For any given applied load sigma naught, the spring can extend only up to sigma naught by r. So, that is given here. So, this strain will reach this particular portion, and then what will really happen? The spring will refuse to extend and the dashpot has to remain as it is. It cannot move because the spring will now restrain the motion. Okay. So, that is how we have to really understand it. Some of the people who work on the foundations of mechanics do not really like this kind of illustration of the viscoelastic response using springs and dashpot, but for undergraduate and graduate students who are being exposed to these kind of concepts at the very preliminary level, such kind of illustrations helps us to understand how the material response is. Okay. So, the same way in which we discussed for Maxwell model, we are going to write sigma 1 is r times epsilon, sigma 2 is eta times epsilon dot, and sigma is equal to sigma 1 plus sigma 2. So, please do this simple algebra. So, you need to write the expression for sigma here, expressions for sigma 1 here, expression for sigma 2, and rearrange the term. You are going to get a model of this particular structure. So, again this is a constitutive relation, again it is not an explicit expression, it is going to be implicit. So, we need to solve this expression to find out what exactly is the manner in which this is going to vary. So, how we do this? We do the creep and recovery test, apply sigma is equal to sigma naught at t is equal to 0, and when we solve this particular equation 20 that is given here, you are going to get a solution of the following form. Again I need to emphasize here that we are not solving this in the most rigorous way, we are solving it in a fairly simple way. So, this is the expression that you are going to get, sigma epsilon of t is equal to sigma naught by r into 1 minus exponential minus r times t divided by eta. Now, please focus your attention sigma naught by r. Now, if you go to the previous expression, what can really happen? So, when the strain, total strain will reach sigma naught by r, it will reach as t goes to infinity, in which case this portion will vanish and you are going to get sigma naught by r here. Now, there is an interesting analysis one can do similar to what we did in the earlier thing. We want to also find out how the time rate of change of the strain varies here. We want to find that out, because what we really want to do is what is the fastest way in which the strain could start evolving in time. So, to find that out, we are going to take the derivative of equation 21, and this is what we will get here. So, if the strain is going to increase at its initial rate of sigma naught by eta, it would cross the asymptotic value at T c given by. So, this is the parameter Tc, and this is called as the retardation time. So, if you write this carefully, so this is going to be eta by r. The interesting thing is the expression here looks exactly similar to the stress relaxation time that we discussed earlier. So, for the Maxwell model we mentioned about the relaxation time, and for the Kelvin model we are talking about the retardation time. We need to understand that when we are using this word retardation, we are talking in terms of the strain, and when we are talking about the relaxation time, we are talking in terms of the stress. Okay. So, let us understand that subtlety very carefully. Again, similar to what we did, what you did as the exercise in the earlier one, you can always find out this is the total strain at T is equal to tau c, what will be the remaining strain that needs to be accomplished, and you should be able to find out that it is only 37%. The solution for this is available in the material in the book by Finlay Ivanaram. Right. Now, what we need to do is we need to understand how to solve this for the creep and recovery, because what we did here is we are applying a load something like this. Okay. Whatever solutions that we have written here for epsilon t, it is just that the time keeps running and sigma is naught is also here. So, how do we really do this? What we are going to do is we are going to appeal to the superposition principle. So, what is this superposition principle? If you recollect what we did earlier, that if you want to apply something like this T1 T and this is sigma naught, we are going to break it into two portions, one in which sigma keeps running forever and another in which at T is equal to T1 we are going to apply a minus sigma naught. So, what you have to do is to go here. So, let us take this particular case here, sigma naught by r into 1 minus exponential minus r t by eta. So, if we have to write this for the particular case, for the loading case, it is going to be sigma naught by r 1 minus exponential minus r t by eta plus you are going to apply a minus sigma naught by r into 1 minus exponential minus r, you are going to say about t minus T1 by eta. So, this is the expression that you have to solve. So, if you simplify all this, you are going to get this particular form. So, this is going to be the full form for t greater than T1. So, when t tends to infinity, the recovery tends to 0, and while some real material will show full recovery, some of them will show only a partial recovery. I suggest that the students who are taking this course try and see whether they could get this particular expression by doing this simple algebra that I illustrated in the earlier slide. Now, similar to whatever we discussed as far as the dashpot is concerned, in which we showed very clearly that one cannot do a stress relaxation experiment. In a Kelvin model, one really cannot do a stress relaxation experiment. Since there is a presence of a viscous element which is connected in parallel to a spring, it will not be easy to achieve an instantaneous strain epsilon naught, and one can do it only by means of an infinite stress. And if you could do that, this is how it is going to be, but what will really happen? The stress in the dashpot will immediately drop to 0 and there will be a constant strain that will remain in the spring. So, this particular model will not exhibit the stress relaxation part. So, let us Now, look at both of them together. So, this is your Maxwell model for creep and recovery, this is the Kelvin model for creep and recovery. Some of the points that we wrote what a model should do, we wanted a specific time dependent creep as well as a time dependent recovery, but that is something that it will not do, whereas this particular model will do that. But you will also notice that while the Maxwell model will show a nice instantaneous strain or a time independent strain, the Kelvin model will not show this time independent strain on loading and unloading condition. So, what we need to do is not use any of these models, because while one model can do a very good job as far as the stress relaxation is concerned, and another model can do some decent this thing about explaining the creep and recovery, both of them are really not useful modeling the response of creep and recovery as well as stress relaxation. For doing that, we need to use what is really called as a Burger's model, and that we will discuss in the next session. So, please go back, look at all the derivations that have been simple derivations that we discussed in this particular lecture, and try and see whether you can rederive them on their own. Also, please answer whether this is a solid model or whether this is a fluid model. So, we are talking about viscoelastic fluid, viscoelastic solid. Try and relate based on the discussions that we had in our earlier classes about the solid as well as the fluid like response of the material. Thank you very much, and in the next class we will be discussing the Burger's model.